Welcome back to Prove It. We are back, and today we are looking at proving that sine is what we call an odd function and cos is what we call an even function, as well as some other properties. Yes, so it's been a few weeks, but there you go. The Prove It series returns, and specifically, we are looking at the fact that sine of minus x equals minus sine of x. That's what we mean when we say that sine is an odd function. And then also, we're going to be looking at proving that cos of minus x is equal to cos of x. And that's what we mean when we say that cos is an even function. You don't need to know those terms of even function, odd function for maths A level, but that is the official way of describing those two properties we've just written. We're going to prove these using algebra because we like to prove things properly. But I'll tell you what, we are going to give you a treat today because we're also going to prove another couple of things on top of that. We're going to prove that sine of 0 is equal to 0, no matter if we're talking about degrees or radians. That fact's always true. And then also proving that cos of 0 equals 1. Again, doesn't matter if you're in degrees or radians. So there we go. 4 things in one video. Amazing. It's worth pointing out we're going to be using these properties in some tutorial videos released soon on this channel, so that's why I've chosen to do this particular topic today, just because I thought rather than just quoting these formulas just out of thin air, it's a good idea to actually, prove them first. But before we continue, yeah, the usual warning for the Prove It series. You're not meant to know these proofs off by heart. And in fact, actually for Maths A level, arguably, you rarely need to use these properties at all. You definitely need to know them for further Maths A level, though. And then actually, I'm saying properties, I'm talking about those top two ones. The bottom two facts, numerical facts, I would expect everybody to know who's taking Maths A level or related courses, because although you can find them out using the calculator, they're just such important values because they're the y-intercepts of those two graphs. I'd expect you to know those things anyway. Right, so the thing is, some of you are probably looking at this video and going, but why do we need to prove these? Because surely they're true because, well, they are. I mean, if you look at the graph of cos x, for instance, then you will see that if you look at the stuff on the left and you reflect it in the y-axis, you'll just get the stuff that's on the right. And that is true intuitively. And similarly, if you look at the graph of sine x, you can probably hopefully see that if you reflect it in the y-axis, that's the same as taking the graph again and instead reflecting it in the x-axis. You get the same result either way, and that proves that sine of minus x equals minus sine of x. But that isn't really proving it. It intuitively confirms it, but it doesn't prove it properly. And because we're on the Prove It series, we prove things properly, and that's what we're going to do today. But some of you also might be thinking, well, what about the definitions of sine and cos? Remember, that stuff is just about going back to triangles and thinking about the ratio between the hypotenuse, and if it's cos, the relationship between the hypotenuse and the adjacent. If we fix our hypotenuse to be a length of 1 and then increase the angle, we can then see what happens to the adjacent, which for my triangles will be the base of the triangle. And if we do that, for instance, as we rotate anti-clockwise, we can see initially the width of the triangle goes from 1 and then decreases from there, and then does a bunch of other stuff if you rotate further than that. Whereas if you go to the start again, instead of rotating anti-clockwise, increasing the angle positively, you decide to increase the angle negatively. So that means rotating the other way, rotating clockwise. And if we do that in the same way, we see the width just also decreases in exactly the same way. So that's why cos of minus x equals cos of x to a certain extent. But then also we can do the same thing to argue what happens with sine. Sine is, of course, the relationship between the hypotenuse and the opposite. And again, if you rotate the hypotenuse around, you can see the height of the triangle increases. Whereas if we rotate clockwise, you can see the height of the triangle increases in the same way. It's just in the negative direction rather than the positive direction. And that's kind of, to a certain extent, why the property is as it is. But we are going to prove it algebraically. So with all that said, what will we need to be able to do what we're going to do today? We are going to need the trig identity for sine of a minus b. a trig identity which has its own separate proof, and that is sine of a minus b equals sine a cos b minus sine b cos a. That is a trig identity, of course, that's in the formula booklet. And then we're also going to use the trig identity for cos of a minus b, which is cos of a cos of b minus sine of a sine of b. Actually, sorry, plus, I lied, plus I just quoted the cos of a plus b formula there. What was I thinking? Anyway, you can see the identity on the screen right now. And then also we are going to be using some other mystery identities later on in the proof. I'm not going to tell you what those ones are, just because that spoils the fun of when they appear, but it's, some much earlier basic trig identities that I'm expecting everybody who watches this video probably does know those identities anyway already. Cool, so starting off with the proving that sine of minus x equals minus sine of x, we can start by realizing that sine of minus x is secretly something we could choose to write as sine of 0 degrees minus x. I've decided to use degrees here. If it was radians, the whole proof would still work. Cool, once we've written it that way, we realize we've got the structure of a minus b appearing there. Our a would be our 0, our b would be our x. And so if we plug those two facts into the identities we were just quoting from before, we would get this. Sine of 0 cos of x minus sine of x cos of 0. And that's great because sine of 0 has a value. Sine of 0 is 0 and cos of 0 is 1. So if we replace those two things, I should say, with the value that they are, then we get this. And of course, that is just going to simplify, funny enough, to minus sine of x. So there you go, first property proven. And then if we try to prove the second property, we can use a very similar trick. Rewrite it as cos of 0 minus x, realize the 0 can be our a and the x can be our b in the cos of a minus b formula, and then place them in that actual identity properly to get this, and then realize, of course, again, that cos of 0 is 1, sine of 0 is 0, so that means we're going to get this, and then that means 1 times cos of x will get us the cos of x, and the 0 times by anything, of course, is 0, so we're just left with cos of x. Nice! But the problem is these proofs are using the idea that cos of 0 equals 1 and sine of 0 equals 0. And again, I don't like just quoting things without showing where they come from. And admittedly, okay, do these things really need proof? As I said, you can go back to triangles to see why these are really true. But interestingly, I thought it'd be good to show that actually these things can actually be proven using algebra too, amazingly enough. So all you've got to do to, for instance, prove that sine of 0 equals 0, regardless of now if you're talking about degrees or radians, is to realize that 0 is the same as doing a take away a. A take away a would be 0. And then by writing it in this way, we can again use the sine of a minus b formula. And instead of having a and b as separate things, we have both letters now being written as a. If we do that, we're then going to end up with sine of a cos of a minus sine of a cos of a. And wait a minute, we're taking away the same thing that we had added there. So therefore, they're cancelling out to get 0. So there you go. That is why sine of 0 has got to be equal to 0. It makes sense now when you look at the algebra. And then what about cos of 0? Well, again, we can do the same thing. We could rewrite that as cos of a minus a, and then plug it into the identity. And then this time, you could need to do a bit of simplifying. Cos of a times by cos of a is just cos squared of a, and then sine of a times sine of a is just sine squared of a. But hopefully you've seen it. OMG, yes, we have the classic identity. Sine squared a plus cos squared a must be equal to 1 by the famous trig identity. And therefore, cos of 0 has got to equal 1. Amazing. There you go. So we have proven sine of minus x is equal to minus sine of x, cos of minus x is equal to cos of x, and sine of 0 is equal to 0, and cos of 0 is equal to 1. Wow, 4 properties, 1 video. I hope you enjoyed that. But something you could have a go at that we haven't proved in this video is you could have a go at proving these similar properties but for tan. The fact that tan of minus a is equal to minus tan of a. And then also you could have a go at proving that tan of 0 is indeed equal to 0. You can probably guess what you'd have to do to prove that if you want to prove it in a similar way to me. It involves using a particular identity, but have a go, see if you can get those results as well. Brilliant. See you in the next video. On the screen in front of you right now, there are some links to some of my other videos. There's a link to another video in the Prove It series in case you're interested. And there's also a link to my other brand new series called Can We Do That? So do check those out as well. Enjoy.